Welcome back to Mechanical Engineering Made Simple Legends, Lesson 4, Fluid Mechanics. I'm your host. Let's uncover what the textbooks only hint at. In reality, fluids reveal the universe's quiet rules. Bernoulli's principle doesn't just keep planes aloft, it shows us how pressure and speed dance together in every breath we take. Viscosity teaches patience. Too thick and nothing moves. Too thin and everything slips away. Reynolds' number marks the boundary between order and beautiful chaos. Misjudge it and water hammer reminds you that even the gentlest flow can strike like thunder when ignored. School gives you the formulas. Life shows you why they matter in the shower that suddenly feels alive, in blood that carries life without freezing, in honey that moves at its own deliberate pace. The difference between memorizing and understanding is the difference between surviving and thriving. Stay with me. We'll turn the invisible forces into clear insight before life teaches the lesson the expensive way.
That is really the perfect framing for today's mission, because we're really taking a hammer to the foundational text today.
Yeah, exactly.
We're looking at the big stuff. Dimensional analysis, flow measurement, the seemingly paradoxical world of ideal fluids.
Oh, the ideal fluids. Right.
Yeah, and of course the absolute mind bender that is compressible flow. But, we're not here to just read equations off a chalkboard.
No, nobody wants that.
Exactly. The goal of this deep dive is to decode them. We want to explain not just what these concepts are, but why they physically dictate whether your design flies or floats or just, fails catastrophically.
Right, because if you spend any time on engineering forums, you see the exact same pain points surfacing daily.
Oh, yeah. Constantly.
You see these young engineers and they're just drowning in Greek letters, right, and partial derivatives, and they're desperately asking for the real-world link.
Yeah, they know the formula for drag, but they don't know how to trust the data coming out of a wind tunnel.
Exactly. So, to you listening right now, today is about bridging that specific gap. We are translating abstract textbook math into, basically, survival skills for the real world. We're going to answer the most popular questions engineers ask online about fluid dynamics.
And, it's a translation that really matters.
Yeah.
A misunderstanding of these principles, it doesn't just mean a failed midterm.
Right.
In the industry, it means multi-million-dollar testing errors. It means malfunctioning jet engines.
Structural collapse.
Yeah, catastrophic structural collapses. The stakes are incredibly high.
So let's ground this immediately. Say you are tasked with building a colossal hydroelectric dam or, a next-generation passenger jet.
Okay, yep.
You can't just build the full-scale thing, turn it on, and cross your fingers, right?
Yeah, you could try, but your investors wouldn't be very happy.
Right. You have to know it works before you pour $1 billion into manufacturing. So you build a scale model, but here's the massive trap that so many people fall into. How do you actually scale the physics?
Yeah, that's the hard part.
You can scale the geometry down, make a tiny plastic plane, but you can't, scale down the air.
And that dilemma right there is the entire foundation of dimensional analysis and the law of similarity.
Okay, so let's unpack that.
Well, nature doesn't care about our human measurement systems, right? Doesn't care if you measure your pipe in inches or meters or nautical miles.
Right. Nature just does its thing.
Exactly. Nature operates entirely on fundamental physical dimensions. So for mechanical systems, those bedrock dimensions are mass, length, and time.
Okay, so mass, length, and time. Let's apply this. If I'm an aerodynamicist and I'm looking at the drag on a sphere, I have this massive list of variables.
You do, yeah.
I have the drag force itself. I have the diameter of the sphere.
Yep.
I have the velocity of the wind hitting it, the density of the air, and the viscosity of the air. That's, 5 different variables I have to juggle?
5 variables. And juggling 5 variables experimentally is an absolute nightmare. Well, think about it. If you want to graph how drag changes, you'd have to run thousands of wind tunnel tests. You had to change one variable at a time while holding the other 4 constant.
Oh, wow. Yeah.
You would be testing forever. It's just not feasible.
And
this is where the Buckingham Pi theorem comes in as an absolute lifesaver.
Okay, the Buckingham Pi theorem. I remember this from school.
Most engineers do.
And it always felt, to me at least, like a mathematical parlor trick.
A lot of people feel that way.
Right, because you just mash variables together, you multiply them, you divide them until all the units magically cancel out.
Yeah.
And you are left with a dimensionless number.
Yep, that's the process.
But how does erasing units actually keep an engineer from making $1 million mistake? It feels like you're losing information.
That skepticism is incredibly common. And it's a fair pushback. It really does feel like you are deleting information by deleting the units. But you are actually revealing the hidden ratios that govern the universe.
Mm-hmm.
Let's look at your sphere example. You have your 5 variables. Let's call that number of variables n. So n equals 5.
Okay, and earlier we said the fundamental dimensions making up those variables are mass, length, and time.
Correct.
Let's call the number of basic dimensions k, so k equals 3.
Perfect. So the Buckingham pi theorem simply states that the entire complex interaction can be completely described by a smaller number of dimensionless groups, specifically n minus k groups.
So 5 minus 3 is 2.
Exactly. 2. That means those thousands of wind tunnel tests you thought you had to run, they can be collapsed.
Wow.
The entire physical reality of a sphere experiencing drag is governed by just 2 dimensionless numbers. When you do the algebra grouping those 5 variables so their combined dimensions cancel out, you get the drag coefficient and the Reynolds number.
Ah, the legendary Reynolds number. Density times velocity times length divided by viscosity.
That is the one. It is arguably the most important of what I call the big 4 non-dimensional numbers in fluid mechanics.
The big 4. I like that.
Yeah. And you have to remember, dimensionless numbers are always ratios of competing forces. So the Reynolds number is the ratio of inertia forces to viscous forces.
Inertia to viscosity. I always try to visualize these competing forces. Like, inertia is the fluid's momentum, right?
Yes,
It's
exactly.
the mass of the fluid wanting to just keep barreling forward in a straight line like a freight train. And viscosity is the fluid's internal friction, its thickness, trying to pull everything together and slow it down like a web.
That is a brilliant way to visualize it. I love that. So if you have a very high Reynolds number, inertia is dominating the web.
The freight train is winning.
Exactly. The flow is fast, chaotic, and turbulent. Think of water violently rushing out of a fire hydrant. The inertia is so high, it literally tears the flow apart into swirling eddies.
Okay, yeah.
But if you have a low Reynolds number, viscosity is winning. The flow is thick, slow, orderly. Laminar flow.
Laminar, right. So think of cold honey pouring off a spoon.
Perfect example. The internal friction keeps all the fluid particles moving in perfectly parallel, smooth lines.
Okay, so the Reynolds number dictates everything when you are dealing with fluid completely enclosed by boundaries, like pumping crude oil through a pipeline,
Right.
or when an object is totally submerged, like a submarine. But you mentioned a big 4. What happens when we aren't totally submerged? What if we are like a ship on the surface of the ocean?
Huh. Then you enter the domain of the Froude number.
The Froude number.
Yeah. This is the ratio of inertia forces to gravity forces.
Gravity is interesting here because in a completely full enclosed pipe, gravity doesn't really dictate the flow pattern the same way, right?
Not really, no.
So why does it matter so much on the surface?
Because of the free surface.
Yeah.
Anytime you have a fluid interacting with the open air, gravity can act on that boundary.
Oh, I see.
Think about it. When a ship pushes through the ocean, its hull physically displaces water, lifting it up against the force of gravity, and that creates a wave.
Right.
Yeah.
Waves.
Lifting thousands of tons of water requires a massive amount of energy, and that energy is robbed directly from the ship's engines. We call this wave-making resistance.
So if I'm a naval architect and I'm designing a new destroyer and I test a tiny scale model in a towing tank, I have to care about the waves the tiny model makes.
You have to obsess over them. If you want the wave resistance measured on your little model to accurately scale up to the real full-size destroyer, you must guarantee that the Froude number of the model matches the Froude number of the real ship.
Or else what?
If the ratio of inertia to gravity is different, the wave patterns will be totally different, and your drag calculations will be completely useless. You'll build a ship that is vastly underpowered.
Wow. Okay, that makes perfect sense. Reynolds is for viscosity and enclosed flows. Froude is for gravity and surface waves. What is number 3?
The Weber number. This is the ratio of inertia forces to surface tension forces.
Surface tension. But surface tension is usually a weak force, right? Like we are talking about microscopic scales here.
Usually, yes. Surface tension is what keeps a raindrop spherical. It's the cohesive force pulling the liquid together.
Right.
But the Weber number becomes the absolute controlling factor when you are dealing with the formation of droplets or bubbles or incredibly thin films of liquid.
Give me a real-world scenario where an engineer is actually sweating over the Weber number.
Jet engine fuel injectors.
Oh, wow. Okay.
Yeah. You have liquid aviation fuel being sprayed into a combustion chamber. You need that fuel to atomize perfectly to break apart into a very specific mist of microscopic droplets so it burns evenly and efficiently.
And if it doesn't?
If the droplets are too big, the fuel doesn't burn completely. You lose thrust and you create soot. If the engineer doesn't balance the Weber number correctly, predicting exactly how the inertia of the spray will overcome the surface tension of the fuel, the engine will fail.
The stakes are incredibly high.
Very.
And the final, the big four.
The Mach number. The ratio of inertia forces to elasticity forces.
Elasticity.
Yeah, which is just another way of saying the fluid's compressibility. It is effectively the flow velocity divided by the local speed of sound.
Yeah.
We're going to dedicate a massive portion of our discussion to this later, but simply put, it governs high-speed flight.
Right.
Push air fast enough, and it stops acting like water and starts acting like a highly coiled spring.
Okay, so this brings us to a massive, painful reality check for engineers. Let's go back to the idea of model testing. I want to construct a hypothetical scenario for you.
Okay, what's here?
I'm an aerodynamicist for an automaker. I've designed a sleek new sports car, and I want to know its aerodynamic drag before we build the factory tooling.
Makes sense.
So I 3D print a beautiful, perfectly scaled 1 to 10 model of the car. I put it in my wind tunnel. I know the real car will drive at 60 miles per hour on the highway. So I turn the wind tunnel fan on, blast the little model with 60 miles per hour of wind, and read the drag force off my sensors. Am I getting good data?
You are getting garbage data.
Garbage data.
Absolute garbage. And if you trust that data, you are walking straight into a catastrophic design failure.
But why? I scaled the shape perfectly. It's an exact geometric replica.
You achieved geometric similarity, yes, but you completely failed to achieve dynamic similarity.
Dynamic similarity. Okay, explain.
Let's look back at the Reynolds number formula. Density times velocity times length, divided by viscosity. Let's assume the air in the wind tunnel is the exact same as the air outside.
Right, slandered air.
So the density and viscosity are unchanged. But your model is 1/10 the length of the real car.
So my length variable just plummeted by a factor of 10.
Exactly, which means your Reynolds number just plummeted by a factor of 10.
Oh, I see it.
The ratio of inertia to viscosity is totally broken. For your 1/10 scale model sitting in a 60-mile-per-hour wind, viscosity is playing a much, much larger role than it would for the full-size car.
So the air literally feels different to the model.
Yes. The air will feel relatively thicker to the tiny model. The boundary layer of air hugging the surface of the car will behave differently. The point where the airflow separates from the rear bumper will be entirely wrong. The swirling wake behind the car will be the wrong shape. Any drag numbers you pull from that test are fiction.
Wow. So the math demands that I fix the Reynolds number. If my length dropped by a factor of 10, I need to increase another variable in the numerator by a factor of 10 to compensate.
That's the math.
So option 1, I crank up the velocity. I take the real car's speed, 60 miles per hour, and multiply it by 10. I blast my little model with 600 miles per hour of wind.
You could try that, but you just traded one problem for a much, much worse one.
What's that?
By trying to fix the Reynolds number, you just shattered the Mach number.
Oh, because 600 miles per hour is getting uncomfortably close to the speed of sound?
Exactly. Mach 1 at sea level is roughly 760 miles per hour. So your little model car is now experiencing transonic airflow.
The air is compressing violently. Shock waves might be forming over the windshield. The air is acting like a spring. The real car driving at 60 miles per hour will never experience compressible flow. So again, your data is completely useless. You cannot infinitely scale velocity without breaking the physics of compressibility.
Okay, I can't increase the length because that defeats the whole purpose of a scale model.
Right.
I can't increase the velocity because I break the sound barrier. The only other variable in the numerator is the density of the fluid itself. I have to increase the density of the air by a factor of 10. But
Yeah.
how on earth do you make air 10 times thicker?
You build a variable density wind tunnel.
A what?
A variable density wind tunnel. This is an incredible feat of engineering. You take the entire wind tunnel facility, the fan, the test section, the sensors, and you seal it inside a colossal steel pressure vessel.
You're kidding.
No, I mean it. A submarine hull, basically. Then you use massive industrial compressors to pump air into the tunnel until the ambient pressure inside is 10 atmospheres. You literally pressurize the room until the air molecules are packed 10 times denser.
Yes. Now, your 1/10 scale model can be tested at a normal 60 miles per hour. The velocity is realistic, so the Mach number is safe. But because the air is 10 times denser, the Reynolds number perfectly matches the full-sized car driving in normal air.
Wow.
You have achieved dynamic similarity. The forces you measure on the model will scale up perfectly to the real world.
That is a breathtaking brute force solution to a math equation.
It really is.
And it explains why aerospace companies and F1 teams spend hundreds of millions of dollars on their wind tunnel facilities. You aren't just beating a fan, you are building a pressurized ecosystem.
It highlights the extreme lengths engineers must go to in order to respect the fundamental rules of scale. And, speaking of respecting those rules, the source material includes a phenomenal historical dive into Ernst Mach himself.
The namesake of the Mach number.
The very same. He was an Austrian physicist in the late 1800s, and he obviously didn't have variable density wind tunnels.
Right.
He had to rely purely on his analytical mind to diagnose the invisible. He used these exact principles of fluid dynamics to solve two massive military mysteries.
Yeah, the first story here is gripping. It takes place during the Franco-Prussian War, around 1870. The French army had deployed a brand new infantry weapon, the chassepot rifle.
A devastating weapon.
And the Prussians were horrified by what they were seeing on the battlefield. When a Prussian soldier was hit, the wounds weren't small puncture holes. They were massive, crater-like, explosive traumas.
It caused an international diplomatic crisis. The international community, led by the Prussians, accused the French of secretly hollowing out their bullets and filling them with high explosives.
Which was illegal.
Highly illegal. This was a direct violation of the recently signed Declaration of St. Petersburg, which banned explosive projectiles under a certain weight. The French were basically being accused of heinous war crimes.
But the French military brass swore up and down that the bullets were solid lead, no explosives whatsoever. It was a standoff, so they brought in Ernst Mach as an impartial scientific investigator to figure out what was tearing these bodies apart.
And Mach approached it not as a weapons expert, but as a fluid dynamicist.
Interesting.
He realized that the chassepot rifle was firing its solid lead bullets at an unprecedented velocity for the era. It was firing them significantly faster than the speed of sound.
And this is the 1870s. People barely understood aerodynamics, let alone supersonic flight.
Exactly. But Mach deduced that the devastation wasn't chemical, it was pneumatic. Because the bullet was traveling faster than the speed of sound, the air sitting in front of the bullet couldn't receive any acoustic warning to move out of the way.
It couldn't get out of the way.
Right. The air was violently impacted and compressed into a highly pressurized, super dense cone, a bow shock wave that rode continuously on the tip of the bullet.
So when the bullet struck a target, the target wasn't just getting hit by a piece of lead. It was getting hit by a solid wall of hypercompressed air.
A blast wave. Mach proved mathematically and experimentally that the explosive-style wounds were caused by this violent pneumatic shock wave shattering the tissue upon impact. It was entirely independent of the solid projectile. He completely exonerated the French government of the war crimes using nothing but fluid dynamics.
It is an incredible application of physics to global politics, and the sources outline a second mystery he solved, this time for the artillerymen.
Yes, the double bang.
Right. Gun crews had noticed a bizarre auditory phenomenon. When they fired an older, low-velocity cannonball, a spotter standing way downrange would hear a single loud bang. Standard stuff.
Sure.
But when they fired a modern, high-velocity rifled artillery shell, the downrange observer heard two completely distinct bangs, separated by a couple of seconds. They thought the guns were malfunctioning.
And Mach applied the exact same logic. He analyzed the speed of the projectile versus the speed of the sound waves. He explained to the artilleryman that the first bang the observer heard had absolutely nothing to do with the cannon firing.
It didn't.
No. The first bang was the bow shock wave, the sonic boom generated by the supersonic shell tearing through the air directly past their heads.
Ah. The shell arrived first, bringing its own explosion of air with it.
Yes. And the second bang was the actual acoustic noise of the gunpowder combusting at the muzzle, which, was traveling at the normal, slower speed of sound and therefore arrived much later. Mach had essentially diagnosed and explained the sonic boom decades before an airplane ever took flight.
He understood what the invisible fluid was doing just by thinking about the physics of compression, which is honestly the perfect pivot for us.
Oh, yeah.
We know the rules of scale, and we know how fluids behave conceptually. But how do we actually pull numbers out of thin air? How do we diagnose the flow in real time? You can't put a mathematical theorem inside a jet engine. We need physical tools.
We must transition from the theoretical physicist's chalkboard to the working engineer's physical toolbox. We have to purposefully interact with the fluid to measure it. And the most ubiquitous tool for measuring velocity, a tool still proudly mounted on the nose of every single commercial airliner flying today, is the pitot tube.
The pitot tubes, they look like little metal spikes or antennas jutting out from the cockpit window, right?
Yeah, that's them. The underlying principle of a pitot-static tube is an elegant application of Bernoulli's equation. It is essentially a hollow tube with a hole pointing straight forward into the oncoming wind and tiny secondary holes drilled into the side of the tube, perfectly perpendicular to the wind.
I always like to visualize the pitot tube like driving down the highway. Imagine you are driving at 70 miles per hour. If you roll down the window, the ambient air pressure you feel just sitting in the cabin, the pressure pushing on your eardrums is the static pressure. It's just the weight of the atmosphere.
Correct. The holes on the side of the pitot tube measure that static pressure because the air slips smoothly past them without ramming into them.
Now, if you stick your arm straight out the window and hold your palm flat against the wind, you feel a massive force pushing your hand backward. That is the air violently ramming into your skin and coming to a dead stop.
And that dead stop is crucial. In fluid dynamics, we call that the stagnation point. All of the kinetic energy of the moving air is instantly converted into pressure energy.
Okay, kinetic to pressure.
The hole, pointing straight forward on the pitot tube, captures this. It measures the total pressure, which is the sum of the ambient static pressure, plus the dynamic pressure caused by the ramming effect.
So the math is incredibly simple. You take the total pressure from the front hole, you subtract the static pressure from the side holes, and whatever is left over is the dynamic pressure.
Exactly.
And since dynamic pressure is directly tied to the velocity of the fluid and its density, you can calculate exactly how fast you are flying.
It is brilliant, robust, and it has absolutely no moving parts. Engineers even modify it for complex, swirling environments. The text mentions a 5-hole spherical pitot tube. Instead of just pointing forward, it has a central hole and 4 holes arranged in a cross pattern around it. By comparing the minute pressure differences across all 5 holes simultaneously, a computer can calculate not just the speed, but the exact 3-dimensional angle and vector of the airflow hitting the probe.
That's really clever. But the source material flags a massive, deadly misconception here. A trap that catches young engineers and has caused real-world aviation disasters.
Compressibility issue.
Yeah, we talked about compressibility earlier. A lot of people treat the pitot tube formula as absolute gospel. They assume air is just air, and the simple subtraction math always works.
That assumption is only valid if the fluid is strictly incompressible. For water, the standard pitot formula is flawless. For a small Cessna flying at 100 miles per hour, the formula is perfectly fine because the air isn't compressing significantly.
But what happens when you put a pitot tube on an Airbus flying at Mach 0.7?
The air ramming into that front stagnation hole isn't just stopping, it's violently squishing. The density is spiking.
Right.
Exactly. The density of the air inside the tube is now much higher than the density of the air outside. The fundamental assumption of Bernoulli's simple equation is completely broken.
So the math is wrong.
Yes. If an aerospace engineer or a flight computer forgets to apply a specific, complex mathematical adjustment called the compressibility correction factor, the pitot tube will overread the pressure. At Mach 0.7, uncorrected data will yield a velocity error of roughly 6%.
6%. That might sound like a rounding error on a math test, but in an airliner cruising at 35,000 feet, you are operating in a very narrow band between your stall speed, where you fall out of the sky, and your overspeed limit, where the aerodynamic forces literally rip the wings off.
A 6% hallucination in your airspeed data can plunge a plane into the ocean.
It is a critical pain point. You must always know the limits of your physical tools.
Yeah.
Now, pitot tubes are phenomenal for steady, continuous flow, but they have a severe limitation. They are sluggish.
Very sluggish.
Right. If you are researching extreme turbulence where the velocity of the wind is randomly spiking and dropping thousands of times per second, the pressure inside a pitot tube physically cannot equalize fast enough to capture that data. The readings just blur into an average.
And to capture high-frequency turbulence, we abandon pressure entirely and turn to thermodynamics. We use a hot wire anemometer.
Okay, this sounds like a piece of mad science. You are literally sticking a burning wire into the wind.
Conceptually, it is incredibly intuitive. You take an impossibly thin wire, usually made of tungsten or platinum. We're talking micrometers thick, far thinner than a human hair.
Okay.
You run an electrical current through this wire to heat it up until it's glowing hot. Then you place this delicate wire directly into the flowing fluid.
And as the wind blows past it, it cools the wire down, just like blowing on a hot spoonful of soup. The harder you blow, the faster it cools.
Exactly. And here's the physics trick. As the metal wire cools down, its electrical resistance changes. If you constantly monitor the electrical resistance of the wire, you can mathematically reverse engineer exactly how fast the fluid must be moving to cause that specific amount of cooling.
Okay, I follow that. But the text outlines two very different ways to run this system, and one of them has a fatal flaw. Let's talk about the constant voltage method first.
In a constant voltage setup, you supply a steady, unchanging electrical voltage to the wire, and you just passively watch the resistance fluctuate as the wind blows. It sounds simple, but it suffers from a massive physical bottleneck: thermal inertia.
Thermal inertia, so like how an electric stovetop takes a few minutes to actually turn red after you turn the dial, and takes 10 minutes to cool down after you turn it off.
Yeah, precisely.
The metal physically can't change temperature instantly.
That is the exact problem. Even a microscopic tungsten wire takes a tiny fraction of a millisecond to heat up or cool down. If you are trying to measure a turbulent eddy that is vibrating 10,000 times a second, the wire's physical temperature simply cannot keep up.
It's just too slow.
The thermal inertia acts as a damper. The high-frequency data gets smeared, lagged, and eventually lost.
So how do engineers bypass the physical limits of metal?
They flip the paradigm entirely. They use a constant temperature anemometer, or CTA. This is the gold standard in turbulence research.
Okay, CTA.
Instead of passively watching the temperature change, you connect the wire to a hyper-responsive, closed-loop electronic feedback circuit. This circuit constantly monitors the wire's resistance, and if the wind blows and tries to cool the wire down even a fraction of a degree,
Yeah.
the circuit instantly, violently spikes the electrical current to force the wire to stay at the exact same temperature.
Oh, so the temperature of the wire never actually changes. You are measuring the effort the circuit exerts to fight the wind.
You measure the current being pumped in. Because the circuit reacts electronically at the speed of light, you completely bypass the thermal inertia of the metal wire. A high-quality CTA system can accurately capture violent turbulent velocity fluctuations up to 100 kilohertz.
Wow.
That is 100,000 distinct velocity changes every single second.
That is mind-boggling precision. But there is an obvious physical drawback to both pitot tubes and hot wires. You are shoving a piece of metal into the very fluid you are trying to measure.
Yes, that's true.
If you are studying the delicate boundary layer over a wing, sticking a probe in there acts like a speed bump. It disturbs the flow and ruins the very phenomenon you are trying to observe. If you want to measure the invisible without touching it, you have to use light.
Which brings us to the laser Doppler anemometer,
Well,
or
yeah.
LDA. There's optical wizardry based on the Doppler effect.
The Doppler effect is something everyone experiences. When an ambulance drives towards you, the sound waves get bunched together, so the siren sounds high-pitched. When it drives away, the waves stretch out and the pitch drops lower.
Light waves do the exact same thing, just at vastly higher frequencies. In an LDA setup, an engineer points a highly focused laser beam directly into the fluid. Now, the fluid itself is transparent, so the laser would just pass right through.
So how does it measure anything?
You have to seed the fluid with microscopic tracer particles, like a fine mist of oil droplets in air or tiny reflective beads in water. These particles are so small that they flow perfectly along with the fluid.
So the laser beam hits these moving particles.
The light hits the particles and scatters in all directions. Because the particle is physically moving through space at the exact moment the light hits it, the scattered light experiences a tiny Doppler shift in its frequency. The color of the light actually shifts by an imperceptible amount.
And the detector catches that scattered light, compares its new frequency to the original frequency of the laser, and calculates the speed of the particle.
Yes, it is completely non-intrusive. Nothing physically touches the fluid but photons. You can map out incredibly complex, swirling three-dimensional vortices inside a glass pipe without ever disturbing a single drop of water.
Okay, so pitot tubes, hot wires, and lasers are fantastic tools for finding the velocity of a fluid at one microscopic specific point in space.
Right, point measurements.
But in heavy industry, say, a massive petrochemical refinery or a municipal water plant, engineers usually don't care about the velocity at a single coordinate. They want to know the bulk flow rate. How many thousands of gallons of fluid are moving through this massive pipe every minute?
To measure bulk flow, we have to manipulate the entire pipeline. We use flow restrictions.
Yeah.
We purposefully choke the flow.
Choke the flow.
The three primary devices discussed in the source text are the orifice plate, the flow nozzle, and the Venturi tube. They all exploit the continuity equation and Bernoulli's principle.
Let's visualize this.
Sure.
Imagine a massive 4-lane highway packed with cars moving at a steady 50 miles per hour. Suddenly, construction forces the highway to choke down to just 2 lanes.
Okay, yeah.
To get the same number of cars through that bottleneck without traffic backing up forever, the cars in the 2 lanes have to accelerate. They have to speed up to 70 miles per hour to clear the restriction.
The fluid acts exactly like the cars. When you install a restriction in a pipe, the area decreases. To maintain the constant mass flow, the fluid must accelerate through the narrow opening. Bernoulli's principle tells us that when a fluid accelerates, its static pressure drops. The kinetic energy goes up, so the pressure energy must go down.
So an engineer simply measures the pressure of the fluid just before the restriction and measures the pressure right at the narrowest point.
You measure that differential pressure, the larger the pressure drop, the faster the fluid must be accelerating, which means a higher overall volume of flow is moving through the pipe. It is a very reliable mathematical relationship.
Sounds simple enough.
But this is where the textbook theory collides violently with corporate budgets. The source material highlights the stark differences between an orifice plate and a Venturi tube. Choosing between them is a massive, real-world pain point for plant managers.
Okay, let's set the stage. I'm a project engineer. I'm building a massive natural gas pipeline. My boss tells me to keep construction costs down.
Classic.
So I look at the catalog and I choose the orifice plate. Why? Because an orifice plate is literally just a flat piece of steel with a sharp hole drilled in the center. It costs almost nothing. You just unbolt 2 sections of pipe and sandwich it in between. It is incredibly cheap capital expenditure.
It is the cheapest option up front. But you will pay for it every single day for the next 30 years in operating costs.
Why?
You have to visualize what forcing a massive column of fluid through a sharp-edged hole actually does. The fluid slams into the flat steel plate. It has to make a violent 90-degree turn to squeeze through the hole. As it exits the hole, the flow violently rips apart from the edges, creating a massive, chaotic, swirling wake of vortices downstream.
It's pure turbulence.
And turbulence is energy being converted into heat. All those swirling eddies are grinding against each other, dissipating the fluid's kinetic energy due to viscosity. We call this a permanent pressure loss.
Meaning it doesn't bounce back.
Exactly. Once the fluid passes an orifice plate, it never recovers its original pressure. If you have a cross-country pipeline with 50 orifice plates installed along it, the pressure drops so severely that you have to install massive, multi-million-dollar pumping stations just to keep the fluid moving. The electricity cost to overcome that permanent pressure loss will dwarf the savings of buying the cheap plate.
So the orifice plate is a budget trap. It's CapEx versus OpEx. Now let's look at the premium option, the Venturi tube.
A Venturi tube is a masterpiece of fluid dynamics. Instead of a flat plate, a Venturi is a large section of pipe that has been beautifully, meticulously machined to gradually taper down to a smooth throat and then incredibly gently diverge back out to the original diameter.
Because it tapers so smoothly, the fluid doesn't slam into anything.
Exactly. The flow doesn't separate. There are almost no swirling vortices. The fluid accelerates smoothly into the throat, drops its pressure so you can take your measurement, and then expands smoothly out the other side.
Wow.
Because the expansion is so gentle, the kinetic energy is clearly converted back into pressure energy. A Venturi tube might recover up to 95% of the original pressure. Your permanent pressure loss is virtually zero. Your pumps barely have to work.
But the upfront cost?
The upfront cost is astronomical.
Yeah.
They are massive, heavy, difficult to install, and require precision machining. The pain point for the engineer is justifying that massive initial capital expenditure to an accountant by proving the long-term energy savings.
It is the eternal struggle of engineering reality versus financial reality.
It never ends.
Before we leave the physical world, let's look at some of the more exotic bulk flow meters the text covers, because they solve some very specific, nasty industrial problems.
Let's start with the rotometer. This is a wonderfully simple, entirely mechanical device.
I've seen these in hospitals, connected to oxygen tanks. It's a clear, vertical tube with a little floating bead inside.
Yes. The tube is slightly tapered, wider at the top than at the bottom. The fluid flows vertically upward through the tube. As the fluid hits the float, it creates aerodynamic drag, lifting the float upwards.
But gravity is pulling it down.
Right, but gravity is pulling the float downwards. The faster the fluid flows, the higher it pushes the float until the drag force perfectly balances gravity and buoyancy. The engineer literally just looks at where the float is hovering and reads the number printed on the side of the glass. No electricity, no complex math, just a perfect equilibrium of physical forces.
That's elegant. But a rotameter only works if you can see through the tube. What if I am trying to measure the flow of raw, corrosive sewage or a slurry of rocks and water in a mining operation?
Yeah, that's a problem.
An orifice plate would get instantly clogged. A venturi tube would get eroded away by the rocks. I need a meter that doesn't obstruct the pipe at all.
For that, you deploy a magnetic flow meter. This device operates on Faraday's law of electromagnetic induction.
Which states that if you move a conductive material through a magnetic field, you generate an electrical voltage.
Precisely. And we apply that to fluid. You install two powerful electromagnets on the outside of the pipe, creating a strong, constant magnetic field cutting straight through the interior. As the fluid flows through that field, it acts like a moving wire. A voltage is induced inside the fluid itself. You place two small electrodes flush with the inner wall of the pipe to measure that voltage.
And the faster the fluid moves, the higher the voltage generated.
Yes. The beauty of the magnetic meter is that there is absolutely zero physical obstruction in the pipe. The pressure loss is absolutely zero. It is immune to changes in fluid density, viscosity, or temperature. It doesn't care if there are rocks or sludge in the water.
But wait, Faraday's law requires the material to be electrically conductive. Water with minerals in it conducts electricity. But what if I am pumping millions of barrels of pure, refined diesel fuel? Oil is a fantastic electrical insulator.
That is the hard limit. A magnetic flow meter on an oil pipeline is an expensive paperweight. It will read zero no matter how fast the oil moves. For non-conductive fluids, you have to pivot to acoustics. You use an ultrasonic flow meter.
Using sound to measure speed, how does that work in a pipe?
You strap two ultrasonic transducers to the outside of the pipe, positioned diagonally across from each other. They act like both speakers and microphones. Transducer A fires a high-frequency sound pulse diagonally across the fluid to transducer B. Then transducer B fires a pulse back to transducer A.
And because they are firing diagonally, one pulse is fighting upstream and one pulse is surfing downstream.
The downstream sound wave gets a speed boost from the flowing fluid. The upstream sound wave gets slowed down, fighting the current. The computer measures the microscopic difference in transit time between the two pulses. It is entirely non-intrusive, zero pressure drop, and it works perfectly on non-conductive fluids like oil or ultra-pure distilled water.
And finally, the text mentions vortex shedding meters. This one feels like harnessing chaos.
It connects beautifully back to the Strohel number from our dimensional analysis discussion. If you place a blunt object like a simple rectangular bar vertically in the middle of a flowing pipe, the fluid cannot glide smoothly around it. The flow separates, forming a swirling vortex behind the bar.
A localized tornado.
But these tornadoes don't just sit there. They detach and float downstream. We call them von Karman vortices. And they shed in a perfectly alternating rhythmic pattern. One peels off the left side of the bar, then one peels off the right side, like a flag flapping in the wind.
And the math shows that the frequency of that flapping, the speed at which the vortices are shed, is directly linearly proportional to the velocity of the fluid.
The meter just uses a small pressure sensor downstream to feel the pulses and count how many vortices hit it every second. It uses the fluid's inherent instability as a highly precise metronome.
It's brilliant engineering, but everything we just discussed, the pitot tubes, the lasers, the venturis, these are tools for observing reality after it has already been built. If I want to design the aerodynamic profile of a brand new airplane wing from scratch, I can't just guess a shape, build it, and laser it. I need to model the flow mathematically before a single piece of metal is cut.
And to do that, we must leave the physical world and enter part 3 of the text. The mathematician's utopia, ideal fluid dynamics.
Let me stop you right there, because this is a topic that caused me and thousands of other engineering students absolute existential frustration.
Oh, I know. I know exactly where you're going with this.
Every single advanced fluid dynamics textbook begins its heavy mathematical chapters by defining an ideal fluid. And the strict definition of an ideal fluid is a fluid that possesses exactly zero viscosity. It has absolutely no internal friction.
That is the definition, yeah.
Why? Why do universities force students to spend hundreds of hours solving terrifying differential equations for a magical, frictionless fluid that literally does not exist anywhere in the physical universe? It feels completely detached from reality.
It is the ultimate source of cognitive dissonance for an engineer. You spend your early years learning how friction ruins everything, and then suddenly the textbook tells you to pretend friction doesn't exist. It feels like academic self-indulgence.
It really does.
But there is a profoundly pragmatic, Brilliant justification for it. Let's revisit our trusty Reynolds number, the ratio of inertia forces to viscous forces.
Okay, inertia over viscosity.
In many of the most critical real-world engineering applications, like a Boeing 777 cruising at 500 miles per hour, or a nuclear submarine moving rapidly deep underwater, the Reynolds number is incredibly high. We're talking about values in the tens of millions.
Meaning the force of inertia is tens of millions of times stronger than the force of viscosity.
Exactly. Viscosity still exists. The air still has friction. But because the massive inertia of the high-speed flow is so overwhelmingly dominant, the physical effects of that viscosity are squashed down and confined to an impossibly thin layer of air located right against the microscopic surface of the airplane wing.
The boundary layer.
Yes. Inside that boundary layer, which might only be a few millimeters thick, friction is a violent reality. The air is shearing aggressively against the metal skin. But step up just 1 inch away from the wing into the vast bulk of the airflow surrounding the plane, and the velocity gradients are so incredibly gentle that the effects of viscosity become statistically negligible. The bulk of the air behaves, for all practical mathematical intents and purposes, exactly as if it had zero viscosity.
So it's a strategic lie.
It is a mathematically necessary simplification. If you tried to calculate the exact true viscous friction of every single air molecule interacting around a whole airplane, the nonlinear math would bring the world's most powerful supercomputers to their knees. By strategically pretending viscosity is zero in the bulk flow, the math becomes solvable. And the aerodynamic lift answers we get from that fake math are stunningly accurate for 99% of the flow field.
Okay, I will accept the premise. Let's unpack the math of this utopia. The text introduces 2 heavy hitters right away, the velocity potential and the stream function. What are these, and how should a visual thinker imagine them?
The best analogy is a topographical map of a mountain.
Okay.
If you look at a topo map, you see contour lines. If you hike along a single contour line, your elevation never changes. You're walking perfectly flat around the mountain.
Right.
Now, if you drop a boulder on the side of that mountain, which way does it roll? It rolls straight down, taking the steepest possible path. Mathematically, the steepest path is always perfectly perpendicular to the contour lines. The boulder crosses every elevation line at exactly 90 degrees.
Okay, I see the mountain. How does this map to fluid?
The velocity potential, denoted by the Greek letter phi, is the mountain's elevation. It represents the invisible field of pressure or energy potential that is driving the fluid. An equipotential line is a line where that driving energy is constant.
And the other one?
The stream function, denoted by the Greek letter ci, is the path the boulder takes. A streamline is the actual physical path that a particle of fluid will follow.
And just like the boulder crossing the elevation lines, the streamlines must cross the potential lines at perfect right angles.
Yes. For an ideal irrotational flow, the fundamental equations of physics dictate that the streamlines and equipotential lines form a perfectly orthogonal grid. Wherever they intersect, they cross at exactly 90-degree angles. This means if you can somehow map out the invisible energy potential, you can mathematically derive the exact physical path the fluid will take. They are 2 sides of the same mathematical coin, firmly linked together by the Cauchy-Riemann equations and governed by the absolute overlord of ideal fluid math, Laplace's equation.
Let's talk about Laplace's equation, because just hearing the name makes engineers sweat. The text says Laplace's equation dictates that the divergence of the gradient of the potential is 0. That is pure mathematical jargon. Translate that into English. What does divergence of a gradient actually physically mean?
Let's break it down into 2 words: gradient and divergence. We know what a gradient is. It's a slope. It's how steep the energy mountain is. A steep gradient means high velocity.
Okay.
Divergence is a measure of whether fluid is spreading out from a specific point or converging into a specific point.
So spreading out.
Right. If the divergence of a fluid was a positive number, it would mean fluid is spontaneously appearing out of nowhere and expanding outwards. If the divergence was negative, it would mean fluid is spontaneously disappearing, vanishing from existence at that point.
But physics says you can't just magically create or destroy mass.
Exactly, the conservation of mass. Laplace's equation stating that the divergence is exactly 0 everywhere is just the mathematical translation of the physical law that mass cannot be created or destroyed. It means that whatever amount of fluid enters a specific tiny box of space, that exact same amount of fluid must exit the box. The flow is continuous, smooth, and unbroken.
Okay, that makes it much less terrifying. It just means the math is behaving itself.
And because ideal fluid flow is governed by Laplace's beautifully behaved equation, it possesses what is arguably the most powerful mathematical property in existence: linearity.
Linearity means you can just add things together using simple addition.
Yes, the principle of superposition. If you have a mathematical formula that perfectly describes flow pattern A, and you have another mathematical formula that perfectly describes flow pattern B, because of linearity, you don't have to invent new math to combine them. You literally just take formula A, add formula B, and the result is a perfectly valid, physically accurate formula for a new, highly complex flow pattern C. This is how engineers modeled complex aerodynamics for decades before digital computers were invented.
Let's walk through the textbook example of this because it shows how something incredibly abstract builds reality. They start with the most basic, cartoonish building blocks imaginable: a source and a sink.
Right. Imagine a perfectly flat, infinite two-dimensional plane. A source is a microscopic mathematical point where fluid is magically welling up from nowhere and flowing radially outward in all directions, like a perfect sunburst. It violates mass conservation at that one singular dot, but nowhere else.
And a sink.
A sink is the exact opposite. It's a microscopic drain hole where fluid is rushing inward from all directions and disappearing from the universe.
Okay, so we have a mathematical hose and a mathematical drain. What happens when you use superposition to add them together?
If you place a source and a sink a few inches apart on your mathematical plane, the streamlines become beautiful arcs. Fluid erupts from the source, curves through space, and dives straight into the sink. It looks exactly like the magnetic field lines looping between the north and south poles of a bar magnet.
And here is where the mathematician's brain takes over. What happens if you take that source and that sink and you start sliding them closer and closer together while simultaneously turning up their strength?
You slide them closer and closer, turning the strength to infinity until the distance between them is 0. They occupy the exact same coordinate. The hose and the drain are stacked on top of each other.
That sounds like it should just cancel out to nothing.
Intuition says they cancel, but the math says they create a singularity called a doublet. A doublet has an incredibly specific, mesmerizing flow pattern. The fluid erupts and immediately loops back on itself. The streamlines form a series of perfect, nested circles that all pass through the origin point and are tangent to the axis. It is a pure, abstract mathematical construct, a circular flow of energy.
But why? Why does an engineer designing an airplane care about stacking a fake hose and a fake drain to make circles?
Because of the next step of superposition. Watch the magic trick. We take the complex equation for that doublet's circular flow, and we're going to add it to the simplest equation in the book: uniform flow. Uniform flow is just wind blowing perfectly straight left to right at a constant speed.
Straight, parallel lines.
When you add the mathematical equation of the straight uniform flow to the equation of the circular doublet flow, the geometries collide. The straight lines of the wind push against the expanding circles of the doublet, and the resulting mathematical equation perfectly, flawlessly describes the complex airflow going around a solid, two-dimensional circular cylinder.
You take a fake hose, a fake drain, blow some fake straight wind at it, and the math spits out the exact blueprint for how real wind interacts with a real smokestack or a real pipe or a real wire.
You are seeing the matrix now. By stacking incredibly simple, abstract mathematical building blocks, we can construct the geometry of physical reality. We bypassed solving terrifying nonlinear differential equations from scratch. We just used basic addition to synthesize a cylinder.
Okay, but cylinders don't fly. Airplanes have wings. They have sleek, teardrop-shaped airfoils. Adding a source and a sink gets me a circle. How do we get from a circle to a Boeing 747?
To jump from a cylinder to a wing, we need one more mathematical tool. It is arguably one of the most brilliant insights in the history of aerodynamics. Conformal mapping, specifically the Joukowsky transformation, developed by a Russian mathematician.
I always struggled with conformal mapping. The text says it maps points from the z-plane to the zeta plane.
Let's use a very grounded analogy. Think about a globe of the Earth. It's a sphere. Now think about a flat paper map of the Earth, like the Mercator projection.
Okay.
The mapmaker had to use a mathematical transformation to stretch, pull, and warp the surface of the 3D sphere onto a 2D piece of paper. Greenland looks massive on the paper, but small on the globe. The geometry is warped, but the mathematical rules linking them are absolute.
Okay, so mapping is just stretching geometry according to a strict rule.
Yes. Now imagine a sheet of incredibly stretchy mathematical rubber. On this rubber sheet, we have drawn the perfect, beautiful streamlines for flow around our cylinder. We know that math works. Conformal mapping applies a specific formula to stretch that rubber sheet, but it is a very special type of stretching. Conformal mapping preserves local angles.
Meaning what?
Remember our mountain topo map? The streamlines and equipotential lines must cross at exactly 90 degrees to satisfy Laplace's equation. When you stretch the rubber sheet, the grid lines bend and warp, but wherever they intersect, they still cross at exactly 90 degrees. The orthogonal grid is preserved.
Which means Laplace's equation is still satisfied. The math is still physically valid. It hasn't broken the laws of physics. It just changed shapes.
That is the genius of it. So Nikolai Joukowsky found a specific transformation formula. When you apply his formula, the solid circle of the cylinder stretches, warps, and flattens out into the elegant teardrop shape of an airplane wing. And all those beautiful, simple streamlines we calculated for the cylinder automatically stretch and wrap themselves perfectly around the new wing shape. We trick the math into giving us the complex aerodynamics of a wing by starting with a simple circle.
It's mathematical alchemy. But the source text points out a massive, catastrophic problem here, a point where the elegant math completely betrays physical reality unless the engineer steps in and forces a patch. Let's talk about the sharp trailing edge of the wing and the CUDA condition.
This is where theory violently meets reality. If you just trust the pure math of the Joukowsky transformation, you get a flay pattern around the wing. The air flows smoothly over the top and smoothly under the bottom. But look at the trailing edge, the razor-sharp back edge of the wing. Remember our foundational assumption. We assumed the fluid was ideal. Zero viscosity, zero friction. It can slip and slide infinitely perfectly over any surface. So what does the pure math say the air flowing along the bottom of the wing does when it hits that sharp back edge?
Well, without friction to slow it down, the math dictates that the air hits the sharp point and whips around it. It makes an impossibly tight hairpin turn, flowing from the bottom surface, curling around the razor edge, and flowing forward up the top surface.
Exactly. And to make a zero-radius turn without friction, the math demands that the velocity of the air at that sharp edge must be infinite.
Infinite velocity.
Yeah.
Which is physically impossible.
It is a singularity. If this happened in reality, airplanes would never generate lift. The flow would just curl around the back and cancel everything out. But in the real world, airplanes do fly. Why? Because our initial assumption was a lie. Viscosity does exist. That microscopic boundary layer of friction. Yes. That tiny, almost negligible amount of friction is just strong enough to prevent the air from making that impossible infinite velocity hairpin turn. The friction grabs the fluid. In reality, the air flowing over the top and the air flowing under the bottom meet at the sharp trailing edge and flow off smoothly together, straight off the back. The trailing edge is a stagnation point.
So the math is predicting infinite curling velocity, but reality is predicting smooth, finite departure. How do engineers fix the math?
They manually hack the equation. Wilhelm CUDA, a brilliant German aerodynamicist, realized the flaw. He said, we must artificially constrain the math so it mimics the friction we ignored. He introduced the CUDA condition. The CUDA condition mandates that the mathematical circulation of air around the wing must be exactly strong enough to force the rear stagnation point, the point where the flow is separate, to sit exactly on the sharp trailing edge.
You mathematically pin the flow to the back edge, forbidding it from curling around.
You force the velocity at the trailing edge to remain finite and smooth. By manually inserting this one artificial rule into the ideal equations, suddenly, the math perfectly predicts the actual lift generated by a real wing. The CUDA condition is the bridge between the mathematician's frictionless fantasy and the physical reality of a 747 taking off. It is the sole reason why airplane wings are designed with sharp trailing edges. If a wing had a rounded back, the CUDA condition wouldn't lock the flow in place. The flow would become chaotic, and stable flight would be impossible.
That is the ultimate lesson. You learn the pure theory, you realize its physical limits, and you use your engineering intuition to patch the difference. And that realization is the perfect transition to part 4 of the source material, breaking the rules compressible flow and shock waves.
Oh, this is the good stuff.
Up until this exact moment, whether we were calculating Reynolds numbers, calibrating pitot tubes, or mathematically stretching cylinders into wings, we have relied on one massive, comforting assumption.
We assume the fluid cannot be squeezed.
We assumed density is a rock-solid constant. Water is famously incompressible. But air, we've treated air like water this whole time. When does that assumption fundamentally shatter? When do we push the limits of speed so far that intuition completely fails?
This is the realm of high-speed aerodynamics, ballistics, and rocket nozzles. Gas is inherently compressible. We all know you can squeeze air into a scuba tank. But the physics dictate that if the gas is moving slowly compared to the speed of sound, the actual physical squishing of the molecules against an object is so minor we can ignore it.
But there is a threshold.
The source material is very explicit about this threshold. An engineer can safely treat air as an incompressible fluid with constant density only up to a Mach number of 0.3.
Mach 0.3. At sea level, that is roughly 230 miles per hour. A fast race car, but a very slow airplane.
Right. At Mach 0.3, the air ramming against the nose of the plane compresses enough that its density changes by about 5%. In the gritty reality of engineering, a 5% margin of error is generally accepted as the boundary of good enough. But once you push the throttle past Mach 0.3, the density changes scale exponentially. The air stops behaving like a gentle stream of water and starts behaving like a massive, heavy, highly tensioned slinky. The rules of incompressible flow do not just bend, they invert.
And this leads us to what is easily the biggest mind-bender in the entire source text. It is a concept that aggressively violates common sense. Let's talk about pipe flow and the effect of sectional change.
The nozzle, the subsonic versus supersonic nozzle. This is where we separate the intuition of a plumber from the intuition of a rocket scientist. Let's start with the plumber's intuition, which we discussed earlier with the orifice plate. Imagine a subsonic flow, water flowing from a garden hose. If you take your thumb and pinch the end of the hose, making the exit area narrower, what happens to the water?
It speeds up. It sprays out much faster and further across the yard. We rely on this every day. It is dictated by the fundamental continuity equation. Mass flow rate must remain constant. Mass flow equals density multiplied by area multiplied by velocity. If the fluid is water, the density is locked. It can't change. So if I decrease the area with my thumb, the velocity absolutely must increase to squeeze that same volume of water through the smaller gap.
That is flawless classical physics. A narrowing pipe, a convergent pipe, forces subsonic fluid to accelerate. Conversely, a widening pipe, a divergent pipe, allows subsonic fluid to spread out and slow down. That makes total sense. Now, let us step through the looking glass into the supersonic regime. Imagine you have a pipe, and you have air blasting through it at Mach 2, twice the speed of sound. If that supersonic air enters a narrowing section of pipe, what happens?
My brain screams that it should speed up even more. It's a bottleneck.
But the math and the brutal reality of physics dictate the exact opposite. If a supersonic flow enters a narrowing pipe, it violently slows down.
Okay. And if the pipe widens, if the supersonic flow enters a divergent section?
If a supersonic flow enters a widening pipe, it accelerates. It goes even faster. Mach 2 becomes Mach 3.
Let's stop and unpack this. This is the pain point. Why? Why does a widening pipe make a supersonic gas go faster when we know for a fact that a widening pipe makes a subsonic gas go slower? How can both statements be true in the same universe?
It all comes back to the variable we finally unlocked, density. Let's look at your continuity equation again. Constant mass flow equals density times area times velocity. In subsonic flow, density was locked. It was a constant. So area and velocity were locked in a simple seesaw relationship. One goes up, the other goes down.
But in supersonic flow, we cross the Mach 0.3 threshold. Density is no longer locked. It is highly variable.
Not only is it variable, it becomes the absolute dictator of the equation. As a highly compressed supersonic gas moves forward and tries to accelerate, its pressure drops rapidly. Because it is a compressible gas, when the pressure drops, the density plummets. It expands violently. Here's the secret to the paradox. In supersonic flow, the density of the gas decreases at a much faster rate than the velocity increases.
Oh, let me run that through the equation. Constant mass flow equals density times area times velocity. If the velocity is trying to inch up, but the density is crashing downwards at 10 times the speed, the right side of the equation is shrinking. The total mass flow is dropping.
But the laws of physics state mass flow must be constant. You cannot destroy mass in the pipe.
So to balance the equation, the third variable has to step up. If density is crashing, the area must increase to compensate and keep the mass moving.
You see it. You physically have to widen the pipe to provide more spatial volume for the rapidly expanding low-density gas, just so it has the room to accelerate. If you tried to narrow the pipe, the expanding gas would have nowhere to go. It would choke on itself, build up massive back pressure, and violently decelerate.
A widening pipe gives the expanding gas room to breathe and speed up. That is incredibly counterintuitive, but mathematically perfect. And this specific paradox is the fundamental engine behind every space launch in history. It is the physics of the convergent-divergent nozzle, famously known as the de Laval nozzle, invented by Gustave de Laval in the late 19th century.
If you look at the business end of a SpaceX Falcon 9 or the old Space Shuttle main engines, you see those massive, iconic bell-shaped nozzles. They are narrow at the top and incredibly wide at the bottom. Why? Because they are manipulating this exact paradox to achieve supersonic exhaust.
Let's trace a particle of rocket fuel through that engine. It starts in the combustion chamber. We mix fuel and oxygen and ignite it.
Inside the combustion chamber, you have created a hellscape of incredibly high pressure and high temperature gas. But the gas isn't moving very fast yet. It is highly energized, but its velocity is subsonic. So step one, we need to speed the subsonic gas up. What do?
It's subsonic, so we use plumber's intuition. We narrow the pipe.
Right. The top of the engine nozzle converges. It pinches aggressively inward. As the area decreases, our subsonic exhaust gas accelerates faster and faster, and its pressure begins to drop. If the aerospace engineers designed the curve of that metal perfectly, the gas will accelerate until it reaches exactly yes. Mach 1, the speed of sound, at the absolute narrowest point of the pinch. This narrowest point is called the nozzle throat.
And reaching Mach 1 at the throat triggers a phenomenon the text heavily emphasizes.
Choked flow is a critical thermodynamic limit. When the gas hits Mach 1 at the throat, it is physically impossible to push any more mass through that specific area under those specific upstream pressure conditions. The throat is fundamentally bottlenecked by the speed of sound. Even if you took the exit of the rocket nozzle and shoved it into the deepest, emptiest vacuum of deep space, dropping the downstream pressure to absolute zero, the mass flow rate through the engine would not increase by a single ounce. The flow is choked. For air, the text notes this choked condition occurs when the pressure at the throat drops to exactly 0.5 to 8 times the chamber pressure.
So we have maxed out the bottleneck. We have Mach 1 gas at the throat. But Mach 1 exhaust isn't going to get a rocket to orbit. We need massive supersonic thrust. We need Mach 3, Mach 4.
So now we cross the threshold. The gas at the throat is Mach 1. To make it go faster, to push it into the supersonic regime, we have to flip our engineering logic. We must widen the pipe. So immediately past the throat, the rocket nozzle flares outwards into that massive divergent bell shape. As the area expands, the supersonic gas violently expands with it. Its density plummets, its pressure drops to match the outside atmosphere, and its velocity rockets to Mach 3, Mach 4, Mach 5 out the back.
Converge to get to Mach 1, diverge to go beyond it. The shape of the nozzle is a physical graph of the math, but rockets operate in the real world. What happens if your math doesn't match the environment? What if you designed your divergent bell perfectly for the vacuum of space, but you fire the engine at sea level, where the thick, heavy atmospheric pressure is pushing back against the exhaust?
Then that beautiful, smooth, supersonic acceleration shatters. If the expanding gas inside the wide bell drops to a pressure that is significantly lower than the heavy atmospheric pressure pushing from the outside, the supersonic flow physically cannot smoothly adjust to the higher pressure. Supersonic flows cannot smoothly feel what is ahead of them, so the flow violently collapses in on itself. This collapse creates a shock wave.
We mentioned shockwaves earlier with Ernst Mach's bullets. Let's define it properly. It's not just a loud sound. It is a physical wall in the air.
A shock wave is a massive, sudden, violent discontinuity in the fluid. Over a distance of a few micrometers, literally the thickness of a bacterium, the physical properties of the gas snap. As a supersonic flow crashes through a shock wave, the pressure skyrockets instantly. The temperature spikes thousands of degrees. The entropy, the thermodynamic disorder of the universe increases massively, and the velocity instantly drops from supersonic down to subsonic. It is an incredibly violent, entirely irreversible thermodynamic collision.
The source material categorizes them. It draws a hard line between a normal shock wave and an oblique shock wave.
Yes. A normal shock wave stands perfectly perpendicular, exactly 90 degrees, to the oncoming flow. It is a flat wall. It is the most brutal, energy-destroying type of shock. It decelerates the flow straight from supersonic to subsonic in one catastrophic hit. You might see a normal shock wave forming inside the bell of a rocket engine if it is severely overexpanded at sea level, which can cause intense vibrations that tear the engine apart.
And an oblique shock wave.
An oblique shock forms at an angle. Think of a supersonic fighter jet like an F-22. The nose of the jet is a sharp wedged point driving into the air at Mach 2. The air can't get out of the way, so it compresses into a shock wave. But because the nose is angled, the shock wave attaches to the tip and sweeps backward at an angle, exactly like the V-shaped wake behind a speedboat. Because the shock is at an angle, the collision isn't head-on, it's a glancing blow.
So it's less violent.
Considerably. It still causes a sudden jump in pressure and temperature, but the velocity drop isn't as severe. In fact, the flow behind an oblique shockwave usually remains supersonic. It has just been slightly slowed down and deflected in a new direction. Supersonic aircraft use carefully designed oblique shocks on their engine intakes to gently step the air down to subsonic speeds before it hits the delicate turbine blades.
There is a detail in the text regarding shockwaves that I find absolutely fascinating. A shockwave cannot propagate upstream into a supersonic flow. It can only be swept downstream. Why is the wave trapped?
Think about what a shock wave or any pressure wave or any sound wave fundamentally is. It is a physical disturbance communicating information through the molecules of the fluid. The speed at which that information travels is, by definition, the speed of sound. If the fluid itself is flowing toward the source of the sound faster than the speed of sound, the wave physically cannot swim upstream.
It's like a salmon trying to swim up a waterfall, but the water is falling faster than the salmon can swim. The fish just gets swept backward.
That is the exact mechanism. This is why when an airplane flies supersonically, the air, 1 inch in front of the nose, has absolutely zero physical warning that a plane is about to hit it. The pressure waves trying to warn the air cannot propagate forward. Instead, all those pressure waves, the sound of the engines, the displacement of the air get swept backwards, piling up on top of each other, bunching into an incredibly dense conical envelope dragging behind the plane.
The Mach cone.
Yes. The tip of the cone is the nose of the plane. The angle of this cone, the Mach angle, gets sharper and tighter the faster the plane flies. And this creates a surreal physical boundary. Inside the cone, trailing behind the plane, you have the chaotic turbulence and the deafening roar of the jet engines. But outside the cone, ahead of that boundary line, there is absolute pristine silence. The air is completely undisturbed.
Until that invisible cone sweeps over your house on the ground, and that massive pileup of pressure hits you all at once as a sonic boom. It is a terrifying display of physics. Now, before we wrap up, the text introduces 2 final, highly specialized concepts regarding compressible flow inside pipes: Fano flow and Rayleigh flow. They sound like obscure corner cases.
They are specialized, but they represent the grim, unavoidable realities of engineering. Everything we just discussed about the perfect, smooth acceleration in a rocket nozzle assumed the flow was isentropic, a theoretical condition meaning perfect, frictionless, adiabatic expansion. But real metal pipes have friction, and real jet engines generate massive amounts of heat.
Enter Fano and Rayleigh.
Fano flow is the study of a compressible gas moving through a pipe with a constant area where the pipe is perfectly insulated so no heat enters or leaves, but there is significant friction against the rough walls of the pipe.
Real-world example: pumping highly pressurized natural gas through a pipeline spanning hundreds of miles across Alaska.
Exactly. The friction of the steel walls creates a constant drag on the gas. What is fascinating and highly counterintuitive is how that friction affects the speed of the gas. If the gas enters the pipeline at a subsonic speed, the friction causes the pressure to drop over distance. But remember, a pressure drop means a density drop. To maintain mass flow, the subsonic gas actually accelerates along the pipe, moving faster and faster toward Mach 1 as it travels.
Friction makes the gas speed up. That is another massive mind-bender.
It accelerates because it is expanding. However, if you somehow forced supersonic gas into that same pipe, the friction would act as a violent brake, causing the velocity to decrease, decelerating down toward Mach 1. Notice the pattern. Fano flow dictates that friction always drives the velocity of a compressible fluid toward the speed of sound. It's a thermodynamic trap. If your Alaskan pipeline is long enough, the friction will eventually accelerate the subsonic gas all the way to Mach 1, at which point the flow will choke and you cannot pump any more gas through the line no matter how hard you push.
And Rayleigh flow. How does heat change the game?
Rayleigh flow strips away the friction, assuming a perfectly smooth pipe, but focuses entirely on heat transfer. Imagine the core combustion chamber of a scramjet engine. You have air flowing through a constant area, and you are dumping phenomenal amounts of heat energy into it by spraying and burning aviation fuel. The thermodynamics dictate a similar trap. If the air entering the chamber is subsonic, dumping heat into it causes the air to violently expand and accelerate toward Mach 1. If the air is supersonic, adding heat causes it to decelerate toward Mach 1.
So whether it is the friction of the pipe pulling on it or the heat of combustion expanding it, the fundamental laws of thermodynamics force compressible flow to constantly seek the sonic barrier. It is a physical limit that aerospace engineers are fighting against in every single design meeting.
And that leads to a final, provocative thought for you to ponder long after we sign off. Today, we have mapped out the bizarre, counterintuitive rules that govern subsonic and supersonic flow. We've seen how density changes dictate the necessity of weirdly shaped, diverging nozzles, and how shock waves form impenetrable physical walls in the sky. But ask yourself, what happens when we push even further? What happens when we transcend supersonic and enter the hypersonic regime? Mach 5, Mach 10, Mach 25. When a space capsule re-enters the Earth's atmosphere at orbital velocity, the friction and compression ahead of the heat shield are so intense that the air doesn't just act like a spring anymore. The heat is so extreme, thousands of degrees, that the air itself fundamentally breaks down. It turns into a searing, glowing plasma. The nitrogen and oxygen molecules physically tear apart, changing the fundamental chemistry of the fluid. The Fano lines, the Rayleigh flows, the ideal equations we discussed today, they all disintegrate. They are just the antechamber to the wildest forces in the universe. At Mach 25, you aren't just flying through air. You are flying through a chemical inferno of your own making, relying on material science to survive the fluid dynamics.
If this helped you even a little, say something. We're putting this out for free, no paywall, no subscription, nothing locked behind a card. That only works if we know it's actually reaching people and doing what it's supposed to do. If you're a young engineer trying to figure this stuff out and this gave you clarity you weren't getting anywhere else, drop a like, leave a comment. It takes 2 seconds on your end, but it tells us this is worth continuing instead of just talking into the void. We are excited for your feedback, negative or positive.